Good evening, ladies and gentlemen. I'm Jeff Badnock, and it's my pleasure on behalf of the Alumni Association Community Lecture Series to welcome you tonight to our final 2019 lecture. And I'm glad we made it. I see the snow didn't keep you away, the sun didn't keep you away. You guys are hardcore, and I love you for it. I'm not going to tell you about turning your phones off because you already know that. We're going to, at the end of the lecture, we'll have our customary questions and answers with our speaker. Do like I'm doing, talk directly into the mic, don't hold it down here, talk directly into it so we can capture your comments on the MCAT recording. And I can announce tonight that the series, if you have friends who might be interested in seeing this, will be rebroadcast on MCAT channel 189 beginning Wednesday, April 1st at 7 p.m., and it will be repeated the following Thursday at 6 p.m., and it will run for 6 weeks just like the lecture series. And there will be copies of the schedule available. You can find it either on the Alumni Association's website or you can find it on the MCAT website. One of the great things about this lecture series is when it wraps up tonight, there will be a reception out in the foyer afterwards. If you brought your ticket, that will get you your wine or beer, and we'll have some food to eat as well. So we'll get through the lecture and then we'll go socialize. Before I get to the next part of it, these lectures don't happen by accident, and they haven't been happening by accident for the last 22 years. This was a program that was started by some people in the community. Ann Boone and Kitty Robbins and Don Hobby were the grandparents of this, and those folks saw the need to do a lecture series like this, and they have been putting it together year after year after year, so it's important that we recognize them tonight. I'm kind of a latecomer to the committee, and I am amazed at the work that they did to lay the groundwork so that we could be here tonight. So big round of applause for those people. And then the final announcement is, what do we want for next year? We'd love to have your input. We'll have surveys out at the reception. If you have ideas or things that you think would be an interesting topic for the lecture series, please let us know. We'll work on it. We have a huge faculty on the campus here to draw from. Let us know your ideas so that we can put together another successful series for next year. And now tonight's poem. This is a good one. The poet, I think, wrote this poem for the sound of the words. Sometimes poets really love sound. Sometimes they like to get into the meaning. This is one, I think, which is centered around the sound. And it's by a poet who was born in India and has lived all over the world. And his name is Raj Arum Magam. And it's called Moon, Moon, Crazy Moon. Moon, moon, crazy moon, natural moon, torn apart and snoozing moon, lovely moon, romantic moon, poor, poor moon, the romance plucked out of its drab surface. Moon, moon, going wild, moon, moon, running away from the earth. Oh, moon, why do you run away from the earth? Does earth touch you in the wrong places? And you've got no body to which one could lodge a complaint about sexual harassment. Ah, moon, moon, temperamental moon, dark moon, glowing moon, sexy moon, old woman, hag of a moon. Moon, moon with the best views of the earth. Moon, 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 put me to sleep and wakes me up in the middle of the night. And one day we'll sleep on the moon and produce babies there. And we'll have the first moonish boys and girls and moonly families. But meanwhile, Moon, moon, driving fanatics and inspiring love and romance and myths. Moon, moon, eerie moon. Moon, moon that presides over love and horrors and evil and good. And naked witches dancing in moonlit groves. Poor moon, moon, the earth moon, not as interesting and dramatic as other moons. Don't get too friendly and drop in. Oh, never drop in. No one invited you, silly moon. No, no, you're not invited home to Earth. Moon, moon, cheese moon, eaten by mice. But still, our dear moon, darling moon, 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 our very own Earth's moon. As we moo, moo like cows, moo, 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 at our own moon, moon, moon. One other note that I did forget, and it's a treat. After the reception, the Western Montana Astronomical Association will have telescopes set up outside for us to look at what is not quite maybe a full moon, but a big, big moon. So that will be fun. And we'll be thanking Nick Wetherington of the Society. I think he's here. Nick, are you here? Wave your hand. There he is. There's Nick. He's going to help us out tonight. So, without further ado and showmanship, let's all welcome Nate McCrady.
Sorry, I like to walk around a little bit when I talk, so I'm going to stand over here on the side. So I'm starting off tonight with one of my favorite photos and one of the most amazing photos ever taken by humans. This is a photo taken by astronaut Bill Anders from the Apollo 8 mission back in December of 1968. And this was one of the first loops around the moon that they did on their mission as they prepared for the Apollo 11 landing that was coming up the following July. So they came around the moon. You can see the moon in the foreground, obviously gray, foreboding, lumpy. Like the idea that you were going to land on this surface in just 7 months, never having done it before, looking at that is startling. But what's, obviously the star of the show here is the Earthrise, and this photo is often called Earthrise. You see the Earth rising above the surface of the moon there to give us Earth, which is a fun thing to say out loud, to give us Earth. The moon phases are opposite, so standing on the Earth at the time of this photo, you would have seen a crescent moon. So as they came over the lip of the crescent moon and faced the givest Earth, you can see Earthrise here. And you can see down just at the bottom, right along the limb, the edge of the moon there, you can see the Sahara Desert of Africa there and the Cape of Good Horn on the bottom left. You can see the Atlantic Ocean, and then just up at the top of the moon, you can make out on its side Brazil and South America. And to the left there, you see the Antarctic. So just an amazing image. I forget which astronaut it was. I should have looked it up. But one of them remarked that seeing the moon, I'm sorry, I can't even say it, orbiting the moon and seeing the Earth like that, they realized that you could just hold your hand up and cover everything that you know. Everyone that you know, everything you've ever done, except, I guess, orbit the moon, you can cover with your hand. Just the startling realization that this is just this little ball that we live on that's out there in space. The other reason I wanted to start with this image is that I'm going to continue on a theme that Nancy started a couple weeks ago with discussion of astrobiology and the search for life in the universe. And I think this is an interesting illustration. Just in this image, you can see in the foreground the moon. It has no atmosphere. Notice the line of the mountains and the cliffs that you see right on the limb, the edge of the moon right there, completely sharp. One of the astronauts commented that moonwalks were a little startling for the astronauts because they'd think, I'm going to go look at that boulder over there. And they'd walk for 5 or 10 minutes and realize that's a mountain that's even farther away than they thought. And it looked small and nearby, but it's far away because there's no atmosphere to give you any depth perception or any sense of how far away anything is or how big anything is. The moon couldn't be more inhospitable to life. It's baked in sunshine. There's no atmosphere. It's completely dark on the nighttime side, absolutely cold on the nighttime side. No hint of atmosphere, no hint of water, liquid, or, there may be some subsurface ice, but not a lot of it if there is. Just a completely inhospitable place. And this is right next door. And just, 2.5 light seconds of travel away, there's the Earth. And look at the contrast there. The Earth is this pale blue dot, to use Carl Sagan's fantastic term. You've got liquid water oceans. You've got clouds that are giving a hint that there's water vapor there. It condenses out into the cloud droplets. And you have the ice caps. So you have liquid water, an essential ingredient in all forms of life that we know of on the planet. All three forms, all three phases of water are evident just in looking at it. 70% of its surface covered with liquid water, which is completely rare in the universe. Water is absolutely everywhere in the universe, but it's generally either in gas form or solid form. Ice is very common in the solar system, but liquid water is rare. You need specific conditions for that. So here's this wonderful planet right there, and right next door, the next world you can get to, completely barren, completely devoid of life. Fascinating. So when we think about the presence of life in the universe, or whether or not there's life in the universe, I'm going to connect to Rob's talks. They put me last, so I feel like I have to take the baton from everybody. So Rob last week spoke about Arthur C. Clarke and talking about 2001: A Space Odyssey, which I actually watched the day after his talk for the first time. I'd never seen it. Fascinating film that I understood more than I might have. So Arthur C. Clarke says, two possibilities exist. Either we are alone in the universe or we are not. Both are equally frightening. So as a scientist, we heard about the poets feeling the moon had been taken away from them. I want to know what the answer to this is. I want to know which one of these possibilities describes the universe that we live in. So let's think about home. So here's home, another view of home, Africa again. So Antarctica on the bottom, you can see Madagascar off the east coast of Africa, the Horn of Africa and the Arabian Peninsula there. Just a wonderful view of our home. Like I said, liquid water, an essential ingredient in all forms of life that we know of on the planet, present in abundance on the Earth, although that's rare. We have weather systems. We have this marvelous atmosphere. If you look at the edge of the Earth, it's not sharp. It's a little fuzzy because of that atmosphere and the blue skies that we see scattering daylight, scattering sunlight around in what we call daylight. So just a wonderful view from space. This is from another Apollo mission, a single image that captures all of the world in it. Land, water, atmosphere, all the sorts of ingredients that you need for life. So we can now, for the first time really in the history of humanity, take a scientific approach, go out and make measurements, and sort of scientifically address these questions that Nancy Hinman was talking about a couple weeks ago, the central question of astrobiology. Is there other life in the universe? Are there conditions sufficient for life elsewhere in the universe? So Nancy took us around the solar system. This is an artist's impression, obviously, of a potential habitable planet, a planet that might be inhabitable, that might have life on it. And Nancy took us around the solar system and looked at some of the marvelous places. And if I had to bet one place, I would say Europa. Europa is the place to go. I have a friend who's a grad student, and he have a bet whether there are squids living underneath the ice on Europa. I don't know how they're going to figure that out, but interesting thought. So there's all these amazing places that Nancy told us all about in our solar system. So tonight I'm going to look more out into the farther term future and where NASA wants to go in 10 and 15 years. And in particular, what we do beyond the bounds of our solar system. What can we determine about whether or not there is life in the universe and where that might be beyond the bounds of our solar system? Okay. So the first question you might say is like, well, what types of worlds would you look for to find life? So I mentioned liquid water would be really great. So you kind of need a planet that's in, we sort of refer to as the Goldilocks zone. Not so close to its planet that the water boils off into a vapor, not so far away that it freezes into a solid ice. We want to find that little region in between, that ring in between, where you're in that Goldilocks zone, where it's just right to have conditions of liquid water. But those planets, in order to maintain liquid water, also need to have atmospheres on them, atmospheres of sufficient thickness to keep the water from boiling off. Water will boil at low temperature in low pressure. If you've ever looked at your Duncan Hines cake, and they have high altitude directions on that, we have less pressure at this altitude, and so water boils at a different temperature, and you need heat to cook your food, not boiling water. So here's an image of this. Land, a solid planet. You need something solid, a substrate. It's hard to imagine what kind of life forms could live on Jupiter, this giant ball of gas with no solid surface on which to lay eggs or anything like that, or find mates or whatever some sort of floating life might do on Jupiter. So we want to look for solid planets at the right distance from their star to have liquid water. And then we want to look for liquid water. Do they have liquid water? Do they have atmospheres? And we are now at a point where we can do that empirically. We can go measure that on other planets. So one question you might have is if we look for planets outside of our solar system, so let's just go look. We have these fancy telescopes that you paid for. Let's go look at them, look at these planets and just look directly. There's a challenge with that. There's a big challenge. This is the sun. Here's an image of the sun. The sun's enormous, but it's sort of a middle-sized star. There are stars that are much bigger than the sun. There are stars that are much smaller than the sun. The smallest stars are about the size of Jupiter, which is about 1/10 the diameter of the sun. So this is sort of a sort of typical star in our galaxy. And you see it's got these little spots on it, and it's this big disk, and it's extremely bright. It's got nuclear fusion going on the inside, and light is shining out of it at prodigious rates. There's a tremendous amount of luminosity coming out of it. My students are waiting for me to say scientific notation, but I'm not going to. So there's one other thing on this image. The other thing on this image is a planet. That is not Earth. That's a dot I put on there, but that dot is scaled to be the size of the Earth. So I wanted to point out the problem that you have with direct imaging, where you want to go out and just take a direct image of a planet. Just go photograph it, if you will. The problem is, that's how big the star is. That's how big the planet is. The star is shining. It's got nuclear fusion going on inside of it, and light is pouring out of it. The Earth, in this case, or some little planet that's the size of the Earth, is merely reflecting the starlight, right? Most of the starlight doesn't hit the planet, and only about 70% of what hits the planet gets reflected. So the ratio of the brightness of the planet to the brightness of the star is about 10 billion times brighter than the planet. The planet's also right next to the star. So the analogy that my colleagues and I tend to use is it's like looking for a firefly while staring into a searchlight. So you've got one of these airplane searchlights just pointed at your face, and you're looking for the firefly. Okay, so direct imaging is not generally the way to go about this. So we have to use more indirect techniques. So here's something familiar, I hope, to all of you. If you pass sunlight through a prism or a candlestick or a crystal, you'll see the sunlight is split into its component colors. So that whole rainbow, in fact, if you pass light through a rainbow, if you pass light through water droplets in the atmosphere, and that bounces back, you get this rainbow spread of the colors of light in the sun. And so here's an example of that. If we look at the sun with more scientific equipment than a piece of glass, you can spread the light of the sun out into constituent wavelengths in very, 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 very thin slices. And so this is the spectrum of the sun. It's like you pass the light through a prism and just spread it out over a long line of different colors, from blue to green to orange to yellow to orange to red. And here we've stacked those on top of each other so you can see it. That's the spectrum of the sun. So you can see the sun gives off almost all the colors of the rainbow, but not all the colors. If you look, there are specific colors that are missing. There are, let's see, a pair of lines right there, for example. Those are the result of sodium atoms in the atmosphere of the sun absorbing light at specific wavelengths. And I could do a whole quantum physics class on you, but I won't. Just take it to be that the sun and other stars have these sort of fingerprints imposed upon them based on the elements that are present in their atmospheres. That's not important why that happens or how that happens for us tonight. It's just important that it happens because we're going to use it. So stars have these imprinted wavelengths on here. We can go in and identify what those wavelengths are. We can figure out what species they are and figure out what the star is made of. That's a really neat talk that somebody else could give some other time. All I'm going to do is use those to tell if the star is moving or not. So here's how that works. When a planet orbits a star, so up here on the top in Alyssa Obert's amazing demo here, the little blue circle going around the orbit there is a planet going around the star. But we always talk about that. We say that planets orbit stars. But in fact, stars orbit planets as well. It's just that the planet has a small amount of mass, and the star has an enormous amount of mass. So when the planet goes around the star's gravity pulls on the planet and keeps it from just shooting off into space. It keeps it moving around in an orbit. Okay? But at the same time, the planet, which also has mass, is pulling on the star. And so the star also moves. And in fact, they both orbit the balance point between them, called the center of mass. That center of mass is usually inside the star. So we think of them both orbiting the center of mass. The Earth goes around in a big circle, and the sun goes around in a tiny circle. And that center of mass for the Earth and the sun is inside the sun. So we call it a wobble. It's like the sun does this. Now remember that contrast ratio that I said. This is 10 billion times brighter than this little thing reflecting a tiny fraction of the light here. So when this planet is going around the star, we don't see the planet, but we do see the star. So we can go in and measure that little wiggle of the star. And as the star wiggles around, the star has a spectrum. Here's a view of the spectrum like I just showed you. And some of those lines on there are representative of the thousands of black lines, the specific wavelengths that are absorbed out of the sun's atmosphere. And as the star moves away from you and towards you, there's a technique, or there's a physical phenomenon called the Doppler shift that causes those lines, the wavelength of the lines, to move back and forth. The wavelengths of those lines change. So when the star moves towards you, so in this diagram, you're down here where I am, looking that way. So right now the star is moving away from me, and when the star moves away from me, these lines get shifted to longer wavelengths. Now the star is going to start moving towards me, and you can see the lines are shifted blue, shorter wavelengths. Now they shift back to the regular point. Now the star is going away from me, and they shift red. So if we watch that red and blue pattern, we can trace out the motion of the star as a result of a planet that we can't even see. So we can indirectly detect the planet. So when the star is moving away from us, you can see its velocity is up here. And when the star is moving back towards us, the velocity goes what we call negative. And it's moving towards me, and now it's going to be moving away from me when it gets back over here. And by watching this pattern over the course of weeks or months, we can watch the orbit of the planet by watching the star move away from us, towards us, away from us, towards us, away from us, towards us. The amount of the speed of the star, I should say, the amount of the back and forth motion of that star depends on the mass of the planet. If there's a more massive planet, you have a more rapidly rotating star. Or a more rapidly moving star, let's say. If the planet is smaller, like Earth, or even smaller, like Mercury, the star moves a smaller amount in response to that. So the mass of this planet is given to us by the amount of velocity amplitude back and forth from the star. So this was first figured out back in the 1990s, and a couple teams of scientists looked at this and said, if we could go measure other stars and watch their motions and see if these stars are periodically coming towards us and away, towards us and away, towards us and away, we could measure how much mass there is in the planet orbiting that star, and we could measure how long it takes the planet to go around once. So from here to there to here again is one orbit of the planet. There's a second orbit. There's a third orbit. Okay. So you could measure the length of time it takes for the star to go around. That's the orbit of the planet. They're always on opposite sides of the center of mass. And the speed tells you how much mass the planet has. So the first successful use of this technique was the detection of the first planet outside of our solar system by a pair of Swiss astronomers seen here. This is Michel Mayor and Didier Queloz. Two Swiss astronomers working in Europe went in and measured. This is not their data, but this is somebody that subsequently has measured this, and basically just going in and measuring the velocity of the star. So each point on here is the speed of the star, away from you, towards you, away from you, towards you. These are just days, so here's 10 days, 20 days, 30 days, 40 days. So they were able to detect this star by the planet's periodic motion of the wiggle as the unseen planet orbited it. Now, one thing you might notice is I said that's 10, 20, 30, 40 days, and I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 orbits in 40 days. Yeah, this is a weird planet. We have nothing like this in our solar system. This planet is orbiting its star every 3.9 days. That's just birthday after birthday after birthday. You're not even finishing the cake, right? So this star is being orbited by a planet that, and I didn't mention, but from the amplitude of that, you can tell that this planet has the mass of Jupiter. So this is a giant gas planet directly next to a star orbiting every 3.9 days. Totally unexpected. Totally easy to find, as it turns out, because it makes the biggest signal on the planet, and it happens over and over again. So you just watch for a little while, and you go, yep, there's the planet. Totally easy to find. We can measure this on the roof over here on campus at this point. So this planet is an example of a hot Jupiter. Those turn out to be kind of rare, but they're easy to find. The nice thing here is that did prove the technique. And very rapidly after this, 10, 20, 40, 50, 100 planets were found like this. Not all these hot Jupiters, but planets were found with this technique. The challenge to find planets that you could put life on, if you're in a 3-day orbit around the sun, you can guess what the weather's like on a planet there. It's hot. Like 1,500 degrees Kelvin. It's 300 Kelvin in this room. Extremely hot. Not good for life. So what you want to do is you want to find Earth-like planets. You want to find rocky planets that are far enough out where you can have liquid water. And to do that, you need to look for like really faint signals, really fine signals. The planet orbits less often, so the up and down is going to be smaller, and it's going to take longer for it to happen. So you've got to really get down in the weeds and look for this. So you have to use some other techniques. This is Deborah Fisher. You'll meet more about Deborah Fisher later on. She's at Yale University. And Deborah's looking at the spectrum of the sun right here, and you can see some radial velocity information behind her there. So this is the sun spectrum. It's pretty similar to what I just showed you, and she's identifying some of the lines in here. What you want to do is go in and measure the positions of those lines, thousands and thousands of these lines. And as the star moves towards you and away from you, those lines shift around. And by measuring these lines to really, really high precision, you can figure out if there's a tiny little Earth-sized planet orbiting that giant star. And to do this, you need the ability to calibrate the spectrum really, really well. And so this man over here, Paul Butler, who detected something like 200 of the first 300 exoplanets ever found. Exoplanet, by the way, is a planet orbiting another star. So Paul and his team over here detected about 70% of the first 300 exoplanets ever detected, highly successful at this. Paul and his team began this technique of using a little glass cell. This is about the size, you can see Paul's holding one up and looking through it here. It's about the size of a beverage can, like a Coke can. And that cell in there has iodine in it, a little bit of iodine gas. And the nice thing is when light passes through the iodine gas, if you pass light through that, you see this wiggly wiggle, wiggle, wiggle here. It gives you all of these little wiggles from the iodine. And the nice thing is the iodine's attached to your telescope. It never moves. So you have all these lines that just sit there because you're looking at the light through the iodine. The planet from the star, the planet's motion causes the star's lines to go like this, but now you don't have to carefully measure the position of these. You just measure them in comparison to the ones that aren't moving. And this technique was a major leap forward. This is, I'll tell you more about this particular cell. Deborah and her team made that cell for us. I'll tell you more about it later on. So this gives us the opportunity to use what's known as the radial velocity technique, measuring the velocity of the star as it moves around its orbit towards us and away from us. That radial velocity technique allows us to try to find these small rocky planets. The ones we're most interested in, of course, are the ones that could harbor life. The easiest ones to find are these enormous gas giants that are right next to the star where it's ridiculously hot. Okay, fine. But we want to use that technique, that Doppler technique, to measure the masses of these planets and find Earth-sized planets that are orbiting far enough away from their sun that they might have liquid water on the surface. Solid planets with liquid water on their surface. So let's talk about that Goldilocks zone for a little bit. That Goldilocks zone, or what we technically call the habitable zone, is that zone where you're close enough that it's not frozen, water's not frozen, but not so close that the water boils off. Now, not all stars are created equal, as it turns out. The sun has a surface temperature of about 6,000 Kelvin, a little less, 5,800 Kelvin. And so here's Earth. Earth is out at 1 Earth distance. So this is astronomical units. Astronomers like to make up convenient units. The distance between the Earth and the sun is 1. How fortunate. So there's the Earth's distance from the sun. It's 1 Earth distance, and the sun has 5,800 Kelvin surface. So you can see on here, after you get out to about 1.4, 1.123 times as far as the Earth is, if Earth was 30% farther away from the sun than it is now, it's too cold out there, and our oceans would freeze. If we were a little closer in, if we were in here at about 0.7, 0.75, it would be so hot that the water would boil off into the atmosphere. Water's a very potent greenhouse gas. It would trap infrared light, and the temperature on the Earth would jump enormously. There is a planet that's right at about 0.7. It's kind of referred to as Earth's twin. It's Venus. It's about the same size. It's about the same mass, about the same gravity, about the same density, made of the same stuff. It's 30% closer to us. And the temperature on the surface of that planet is about 900 Fahrenheit. Because there's so much trapping of infrared light that the temperature is extremely hot because of the runaway greenhouse situation on Venus. So we have this narrow little range here. Earth, worrisomely, is on the inner edge of that habitable zone. If it got much warmer here, we could have problems if we were much closer. Fortunately, our orbit doesn't change. So we're in the habitable zone clearly, but just barely. If you look at other stars, like a really hot stars dump out an enormous amount of light. That's like a really hot campfire. You can't stand as close to it. You have to back up a little bit. So the habitable zone is farther away from these stars. Conversely, a low mass star, which is also a small star, which is also a very cool star with the surface temperature of only about 3,000 Kelvin, the habitable zone just hugs right in against the star. And that's going to be important. These M-class stars, our sun's a G-class star if you're keeping score at home. The M-class stars, these little cool red stars that are about the size of Jupiter, by the way, the habitable zone is right next to those stars. So bear that in mind. We're going to come back and talk to that. So I mentioned Deborah Fisher earlier. So Deborah at Yale and her team studied the 55 Cancri system. So planets were being discovered, and along in about 2007, Deborah and her team announced the discovery of the 5th planet around orbiting the star 55 Cancri. Astronomers give these amazing names. There's 55 Cancri b, c, d, e, and f. So F was the 5th star orbiting this. Talk about stealing something from the poets. The poets need to help us. We need good names for these planets. So 55 Cancri F, you can see B, C, and E are here. D is out here, way out on the outside. It's very hot in here where these 3 planets are orbiting, but Deborah and her team announced the detection of 55 Cancri F orbiting out here, farther out. That's in the habitable zone. That's in that region where you could have liquid water on the surface. Sadly, 55 Cancri F doesn't have a surface. 55 Cancri F is about Neptune-sized. These are kind of, you can see here's our solar system. It's in Spanish. Si hablas español. And I just like the plot. But 55 Cancri F is more like Uranus or Neptune-sized. It's about half the mass of Saturn. So it's a gas giant of some sort. It's kind of a Neptune-like planet. But the thinking is it probably has exomoons. And Nancy told us about these great places in the solar system, Titan specifically, Europa, Enceladus, which I'll talk a little bit more about later on, solid surfaces that are orbiting 55 Cancri F. Maybe, we don't know if it has moons, what we would call exomoons, a word I just love. If it has solid exomoons, there could be life evolving on those, just like Jupiter and Saturn. The moons of Jupiter and Saturn might, except the moons of Jupiter and Saturn are out of the habitable zone. Liquid water could exist on moons orbiting this planet. That's a nice little frontier. Now, I mentioned the size of the habitable zone depends on the brightness of the star. So the more massive stars are brighter stars, bluer stars, hotter stars. They have the large habitable zone. The cooler stars have less power. They don't shine as bright, and they don't give off as much light. So you've got to stand closer to that dim fire to stay warm, to keep your water liquid in the green habitable zone there. But the interesting thing is, as I mentioned earlier about those hot Jupiters, those planets, those big planets, were really easy to detect because they were close into the star. And the closer the planet is to the star, the easier it is for us to detect. There's a stronger gravitational pull, and there's a second effect I'll talk about in a minute. So if you wanted to find habitable zone planets, these M-dwarf stars, these little red cool stars, are really interesting because the planet would be really close to them, and that's where it's really easy to detect them. One of the other things that happens here is if you look at an Earth-sized planet and compare it to an M-dwarf star, so you have a little solid rocky planet, put it in the habitable zone, put it next to one of these dim red M-dwarf stars, it's only about 1/6 to 1/10 of the radius here. You remember when I put the Earth next to the sun? It was that little dot next to that big ball. You could grind up 1,000,000 Earths in your veggie bullet and pour them inside the sun. The sun's huge. But these little M-dwarf stars are Jupiter-sized. And so a little Earth-like planet would be about the size of that star, and that leads to a much bigger signal that we can detect more easily. So these M-dwarf stars are very interesting. So I see some NASA shirts in the room tonight. So let's talk about what NASA is doing in terms of exoplanet exploration. So I'm going to talk about a number of the self-study things that we do in astrophysics. NASA put out in 2004 the Vision for Space Exploration. And that included a bunch of different things. This was during the George W. Bush administration, and this was their sort of direction document for what NASA should be doing at this point and going off into the next 20 years. And the line that I want to mention out of this 4 or 5 page, 6, 7 page report was to conduct advanced telescope searches for Earth-like planets and habitable environments around other stars. So this was the directive that came down from on high. The Bush administration said this is one of the things that we should be doing, and NASA's role was to put that in place. And execute it. So what NASA did then is come up with a 3-stage, what we call the roadmap, the 3-stage roadmap to find habitable zone exoplanets in the nearby galaxy. So 3 steps. 1, figure out the statistics of exoplanet systems. Are they out there? We've found some, so we know they're there, but how common are they? Did we just, are the ones that we found the only ones we found just because that's what they're? Are there more difficult things that we should use different techniques or a higher precision to find? What's out there? How common are these? How easy would it be to find them? Just do a survey. Just look around. It's a census of our galaxy. Do a census and see how many of these things are out there. Step 2, once you know how many of these sort of planets, how common these planets are, is can you find terrestrial, Earth-like, solid planets orbiting around nearby stars? The nearby stars are interesting because they're the easiest ones to study. We get the best signal from them. They're the brightest in our telescopes. They're the ones that we can study most clearly with the spectra of their atmospheres, as I'll talk about in a minute. So let's go look for rocky planets around nearby stars. And then the third and final step is let's go, once we find those planets, let's characterize them. See what those planets are like. See if they're in the habitable zones. and in particular, see if there are signs of life. See if they're the biosignature gases that Nancy taught us about 2 weeks ago. Okay, so let's look at that first step. So this was in about 2005-06 where this roadmap was set up. So the first step, you've heard of Kepler. Kepler, a magnificent mission, one of the best telescopes NASA's ever built. That's Kepler in the upper right there. Mission scientist, the lead scientist, Natalie Battaglia, responsible for so much of the science that came out of this, so I wanted to highlight her excellent work on this amazing mission. What Kepler did, so here's a painting, a NASA painting of our galaxy. So here's the center of our galaxy. We're about 25,000 light years out in a suburb out here, one of the spiral arms called the Orion arm. And what Kepler did is stare at this little part of sky here. So they drew a little cone here, and it's looking at this little region of sky over here, this tiny little region, the Milky Way. So Kepler was a statistics mission. This is doing that census. Let's go measure what's out there and see what exoplanets are out there. So let's just go stare in a spot where there's lots of stars, and let's see how many planets there are. That was the mission that Natalie and her team set up to go detect these planets. So the way they did this, which is clever, this is the Milky Way. So you can see this stripe of the Milky Way. If you go up to the Bob Marshall in the summertime and go out of your tent in the middle of the night, you'll see this amazing stripe of light over the top of your head. If you put your binoculars on it, it's all stars. It's not fuzzy light, it's all stars. You just can't see them apart with the naked eye. So you've got this huge stellar density here. You're looking right in the plane of our galaxy. So what they did is they took their 92 cameras. Each one of these rectangles is one of their cameras. 46 pairs, 92 cameras in total, each one at megapixels. So just an amazing array of detectors on their instrument. And they pointed at this part of the sky. And every 29 minutes they took a picture, and they did that for 4 years. Okay, this is an amazing data set. What they did is just stare at this. There are over 1.5 million stars in there. There were so many stars in the field, they couldn't monitor them all. So what they did is they picked their favorite 1.6 million stars. Out of that 1.6 million stars, they picked their favorite 200,000 stars and monitored them every 29 minutes. And here's the way they're trying to find planets. This is a different technique. This is known as the transit technique. So the idea here is if you happen to have a planet orbiting a star, and that orbit is tilted just right so that the star, when it comes around, comes between you and the planet comes between you and the star, the planet, which is opaque, you can't see through it, will block some of the star's light. So here's a planet cruising around the star on its orbit. As it comes around here, it crosses right between us and the star, blocking the star's light for a little while as it cuts across. And there are two planets that do this in our solar system. Mercury and Venus both cross between the sun and us, and so occasionally you get this little dip in the sun's light. It lasts for 5 or 6 hours as Venus cruises across the surface of the sun. The challenge is the sun gets about 1/10,000th as bright as, less bright. It's 999 10,000ths as bright when Venus is in the way, so it's not like you're like, it's dark out here. So when the planet crosses in front, if you just measure the brightness of the star, measure the brightness of the star, measure the brightness of the star, when it starts blocking the light, you'll see the light from the star dim by some small amount. And then when the planet moves out of the way, you see the star's light again. And so we measure the light curve. And this event, when this planet crosses in front of the star, is known as a transit event. The planet crosses in front. It's like an eclipse, or an occultation, technically. So Kepler did this, and they went out for all these stars, and every 29 minutes they measured the brightness of these couple hundred, 250,000 stars. And they watched them to see if there were any planets detected here. So here's kind of the state of play before Kepler. There had been about 400, it may have been 500 exoplanets detected. I didn't look up the numbers. So this is a little plotty plot here. It's showing, here's the orbital period, 1 day orbital period. That's real fast, 10, 100. You're here, 365. Mars is over here. This is getting Jupiter-like out here. And then this is the mass of the planet. So Earth is one Earth mass at 365 days. So Earth would be right here on this plot. This is all the planets that have been detected. Notice there's nothing detected down here that's sort of Earth mass at sort of like habitable zone distances. That's a hard signal to detect, and nobody had detected these at this point. So that's what we knew about. Most of these are from the radial velocity method. If you notice the colors there, there's a mixture of these little, I guess they're blue and pink, the transits and the radial velocities. These ones are the radial velocities, and you can see that's a lot of them. So that's before Kepler. Kepler, 4-year mission, 4,770 planets. Fascinating. Now, Kepler doesn't measure mass. So notice this plot is mass against the orbital period. This is orbital period against radius. There's kind of a correlation, but it depends on what the planet's made of, which we'll talk about later. But again, this is sort of Jupiter's radius. We have 2 planets like this. They're out here. Jupiter is over here, and Saturn's over here somewhere. We have Neptune and Uranus are about this size, but they're way over here because they're out at very long orbits. Neptune takes 80 years or something to go around the sun. Earth, 365 days. Earth would be right here. Notice Kepler can't detect Earth. If you see here, there's kind of, you can draw a line here and a diagonal line here. Things that are small or far away are hard to find. So things that are small and far away, like Earth, are real hard to find. So Kepler couldn't really find those. It found a few things smaller than Earth, but notice they're in like 100-day orbits or 5-day orbits. But the interesting thing on here, 4,700 exoplanets. When many of you grew up, there was 9. Then there were 8. Now there's over 6,000 planets. Talk about not having names. This blob, the place where we have most of the planets, most of them are bigger than Earth and smaller than Neptune. We have exactly this many planets like that in our solar system. The most common planet found by Kepler is something we'd never seen before. We call them super-Earths. So here's a histogram, if you want to get all sciencey here. Here's sort of supergiant, giant gas giant things. Here's Jupiter-sized things. These are actually pretty rare. Those would be easy to find. Big planets make big signals. They're easier to find. And notice, we didn't find many of them. That's definitely telling us that small planets are more common. Well, that's neat if you're looking for life, because we find life on Earth, a small rocky planet. Here's Earth-sized planets. They're a little hard to find. We found a bunch of them, things that are no more than 25% more than the Earth's size. But then there's this like bulk of the planets from that previous diagram, like sort of 2/3 or more of them in this sort of super-Earth or Neptune-sized object. Now, a lot of these are going to be gaseous, like Neptune, so those are pretty common. But these are fascinating, these super-Earth planets, and I brought a little picture of some super-Earths for you here. So here's Earth. These are artwork. Uranus is a real photo. That's from Voyager. There's Earth, one of the NASA photos, again, the Africa side, or good side, I guess. And then you have some of these planets. Here's a couple of the Kepler planets. Here's 55 Cancri E. I showed you F earlier. And here's another planet orbiting a star called GJ1214. There you go. And you can see that these are all between 1 and 4 Earth radii. We don't have a real working hypothesis of how these planets are formed. We don't see things this size in our solar system, certainly not in these nearby orbits. So this is one of those amazing points for a scientist where I was like, let's go measure something. Did we find it? Yes. What is it? Holy cow, what is that? That's dump trucks of grant money waiting to happen right there. Okay, so what were some of the big takeaways from this statistical mission? We did this survey of just this little. We went to this dense area with a lot of stars and just looked at them for 4 years and said, what did Kepler find? So I want to highlight the results of a couple scientists. This is Courtney Drussing, a professor at Berkeley. Go Bears. So Courtney and her graduate advisor, Dave Charbonneau at Harvard, identified that the typical M dwarf, those little stars, those little red stars, on average in the Kepler survey had 2.5 planets apiece, just the ones they detected. And about 1 out of every 6 of those had an Earth-sized planet in the habitable zone inside that M dwarf star. There's a bunch of worlds right there. These M dwarf stars are the most common star in our galaxy. There's over 100 billion of these stars in our galaxy. On average, 1 out of every 6 of them has a habitable Earth-sized solid planet orbiting in that Goldilocks zone. Worlds. Eric Pettigura here, a Berkeley graduate student, go Bears. 22% of sun-like stars, so these bigger sun-like stars, those big ones that have the little Earth dot next to it, have a habitable Earth, an Earth or super-Earth rocky planet orbiting in the habitable zone. Here's just a quick display of some of those. This is a little bit different axis here. One here is like a nice sunny day on the Earth. This is less sunny than the Earth. This is 5 times as sunny as a sunny day on the Earth. So you're sort of saying, how warm is it on the planet? So again, it's just another way to look at the habitable zone. Stars that are, you don't want to get much warmer, the oceans will boil off. You get much colder, it freezes. There's a number of planets in here, and the ones labeled there with names are Kepler planets. All these pluses on here are Kepler planets, but most of those are giant planets. So there's Earth. There's where Earth is, sun's temperature, sun's flux. There's Earth. And so these are mostly super-Earths. Notice they're bigger than Earth. That's about Earth size. That's about Earth size. That is. But Kepler found a few of these. The problem with these stars, though, is that these stars with these planets are fairly far from us. Remember, Kepler was just a statistics mission. It's just a survey. Let's see how common these things are. So they went and stared at this one point and did good statistics. It's just a place where there were a lot of stars to look at. But it's that one little part of the galaxy. We'd really like to find nearby stars. These stars and their planets are mostly like 1,000 light years from us. We'd like to find things that are like 5 to 50 light years from us. Unfortunately, nature spread those all over the place. They're not just over there in a lump that would be really convenient for us to look at. So stage 2 in the roadmap, then, is to go say, what are the terrestrial planets around nearby stars? So for that, NASA came up with a mission called TESS. This is the Transiting Exoplanet Survey Satellite. So TESS, seen here, has 4 cameras, and they're measuring the sky. TESS is mapping the sky. The plan with TESS, this is sort of like, imagine the sky as the inside of a big glass sphere around us. It's a very Aristotelian way to think about the stars. So imagine this big star, crystal sphere of the sky around us. TESS is right at the center of the sky. And it's just going to go along and take picture, and just paint its way around the sky and do the full sky and do this over the course of 2 years and look at 200,000 stars all around the sky, but stars that are close to us, stars that are 50, 100, 200 light years away, not 2,000, 3,000 light years away, nearby stars, and look for the terrestrial planets on these. I'm going to go fast with this one, but you can look it up online. TESS launched last April. Here's the launch on it's up here in the little payload bay of the rocket here. Successful launch. As of this morning, when I looked, TESS has discovered 8 planets already. They got up there. They've been up less than a year. They did a bunch of calibration and testing and getting ready to go, and their survey has started, and they're just working their way around the sky. And it'll take 2 years to do the whole sky, and they've already detected 8 planets. So there's some excellent papers out there. I'll highlight a couple of them. A paper by Peter Sullivan here, who identified that TESS is going to find 1,700 planets, including over 550 that are smaller than 2 times the radius of the Earth. So these are small rocky planets in the habitable zones of their stars. We've got a handful of those from Kepler, but these are close, nearby ones, 550 of these nearby. Sarah Ballard right here, Berkeley grad, go Bears, went through and found over identified that there are going to be over 1,270 planets orbiting just those small, cool M stars. And this is a plot from Sarah's paper. She was studying what can TESS find and what can TESS not find. So she used Kepler statistics about what kind of planets there are and built systems in her computer and said, okay, let's put planets that are similar to the Kepler planets. The black ones are the ones that TESS can detect. The red ones are ones that TESS will miss because it will be too small of a signal for TESS to find. And so Sarah's outcome, this is a paper from a month ago, she says, oh, even when TESS finds these planets, you should go in and follow up on those planets with other techniques at higher precision and see if you can find even more planets. TESS is going to find, thousands of planets, especially ones that are really interesting in these habitable zones, but it won't catch all of them. So TESS is going to be dumping planets into your news feed for the next couple of years, which is really exciting. This is similar to a plot or it's at least something that Nancy talked about in hers. A couple of great places in our solar system for life. These aren't quite to scale. Enceladus is a little smaller than that. But you see these cutaway diagrams. This is very geophysics or astrophysics textbook kind of thing to do. Like, what's inside these planets? Let's slice it open. Looks like a golf ball in there. You've got some rocky material. You've maybe got an ocean, and you've got an ice cap on the top, whereas Europa is more interesting. It's got rock. It's got metal. It's got an ice layer on the outside, maybe some liquid water, maybe squids on Europa. And so how do we know that is the question. Well, to know that, you want to know how much mass the planet has and what its size is. So if you imagine a shoebox, you could have a shoebox and pick it up and say, whoa, this shoebox is really heavy. You could have an equally sized shoebox, pick it up and go, this one's really light. This one's maybe full of cotton balls. This one's maybe full of sand, right? That density is going to give you a hint as to what's inside. And so we can look at these and say, oh, Enceladus is a density of less than rock, but more than ice, so it's made of a mixture of rock and ice. Whereas Europa must have metal. Metal's more dense. It's generally iron, some nickel. Iron and nickel must be present in the core to make the total density more than just what you'd see from rock and a little bit of ice layer on the outside. So if you want to know what a planet is made of, specifically if you want to know if it's a gas giant or a rocky planet, a terrestrial planet, you need mass and radius. So TESS and Kepler only give us radius. We need another technique to give us mass. You know what it is. We're going to use the Doppler technique. So astronomy every 10 years does what's called these decadal surveys. We go through and say, Congress is going to allot us a certain amount of money. Let's decide among ourselves what to ask for and agree on that first so we're not fighting each other for this money. Let's make a decision as a consensus as a field of what we should spend the money on. And one of the key things in the last decadal survey, the 2021 is underway right now, was to improve the precision radial velocity method. We really want to create dedicated ground-based telescopes with high-resolution spectrometers. The goal there is to be able to measure the masses of Earth-sized planets and super-Earth-sized planets. So my colleague John Johnson, who went to grad school with me, you can guess where, John had this idea. We can answer this call from the decadal survey if we build a set of telescopes that are dedicated. They only study exoplanets, and we go measure the spectra of exoplanets. And so John came up with this idea, and he needed partners. It was going to be 4 telescopes. He needed 4 universities. He found 4 universities. My colleagues at the University of Southern Queensland, Penn State, and myself joined John and his team at Harvard. We each bought a telescope using, in my case, NASA funds, and we built John's vision out on top of the mountain. So this is, I'll just go to the next. This is a lovely picture, but I'll go to the next one. You can watch him move around. So this is our telescopes. This is the Minerva telescope array down on Mount Hopkins, a mountain about 35 miles south of Tucson. We're looking south in this picture. That's Mexico. Nogales, Mexico is right there. This is our 4 telescopes. So that's Montana's telescope right there. These 4 telescopes are used every night robotically. They take data while we sleep. I wake up in the morning, I have my mug of tea, and I read an email that says what I observed last night while I was asleep. Recommended. This is a related telescope in front here. This is run by our colleagues at the University of Pennsylvania. They do a slightly different project than us, but we're showing off a little bit here that we can move all these telescopes in concert. We should have been playing the Blue Danube. Would have been perfect. Thank you to Kubrick. Okay, so there's our telescope. First thing I got there, to the great pleasure of my dean, Jenny McNulty, who got to come down and see this, is I put bumper stickers on it. And all my colleagues showed up and was like, that's a great idea. So they all have them now, but we were first. So here's our telescope. We're not quite at the summit of Mount Hopkins. The multi-mirror telescope is up there. We're down a little bit below the summit on a ridge, which is nice because it keeps us out of a lot of the wind. So this is me up towards the summit. That's our site right there. You can see this beautiful Arizona mountainscape down here. We can see much more of the sky than you can see from Missoula because we're closer to the equator, but also it's not cloudy there. We get about 270 clear nights a year. And my students have been very active in this project. This is one of our recent graduates from the Department of Physics and Astronomy. This is Audrey Houghton down opening up the telescopes for the night when we were down there doing some calibration data. Just quickly mention that we also have a new site that's going in Australia called Minerva Australis with as many as 10 telescopes. I think we're at 6 right now. Here's the Google overhead view of the pads. I think we have 6 telescopes out of these 10 in here since this photo from Google. And that's my colleague Rob Wittenmeyer down at University of Southern Queensland, and then our colleague at the other universities putting these in. And our goal is to go in every night robotically, look at the planets detected by tests that give us the radius. We'll go measure the mass, and that gives you composition, so we can go identify which planets are the rocky planets. Okay, so that brings us to the third step, and this is where we start to head to the future. TESS is up right now. It's orbiting for the next 2 years. It's finding these planets. Minerva is running right now. There's also a planet project called HARPS at Harvard, and there's one at Yale called Chiron, and a couple other projects that are doing things similar that we're doing the radial velocities and measuring the masses. The next phase on the roadmap, phase 3, is we're just getting underway. We as a field and NASA are just moving in this direction to characterize the planets and actually look for life outside our solar system. So one of the things you want for life is you want to look at the atmospheres of the planets. And that's one thing if you're looking at Titan, like you see in this image, if you're looking at Earth, obviously, and that's kind of it. That's I guess Venus has an atmosphere, but Venus is awful. So it's just way too hot. There's sulfuric acid clouds. Venus is totally terrible. So we want to go look at these planets and see if we can understand their atmospheres. And particularly, can we look for gases that tell us the presence of life on those planets? So here's one of my absolute heroes in science. If you want to go read a science paper, look up Sarah Seeger and find something Sarah Seeger wrote. She's amazing. She's at, I don't even know, Johns Hopkins University, I think. Absolutely amazing scientist. I don't know how she seems to have 3 times as much time in her day as I do. But from a paper that she did with William Baines, here's an idea of how this works. We can use this transit technique when a planet goes in front of its host star and blocks the light. The planet is ringed by an atmosphere, and just like you saw in that picture, Titan is a rock, so you can't see through the rock, but the atmosphere is partly transparent, and it's differently transparent at different wavelengths, and that tells you about what's in it. So here's some sciencey looking stuff, but like there's methane, and there's water, and there's methane in water, and Like here's oxygen over here. And so these are models, but different models. And this is, I think Nancy may have shown a plot like this, something similar to this. But the idea is go look at spectra and see if you can find molecules that tell you about the presence of life. I mean, water's everywhere, so water doesn't necessarily tell you anything. But things like methane, some sulfur compounds, ammonia, some things that might be the result of life, signatures of life. And this transit technique that Sarah Seeger has pioneered gives you the opportunity to go take the spectrum as the planet passes in front of the starlight passes through that atmosphere, and it imprints the presence of those molecules on the atmosphere. So here's an example from a nice paper by Maggie Turnbull from the Space Telescope Science Institute. You'll meet Maggie in a minute here in my talk. And so as we go from short wavelength to longer wavelength, you can see all these wiggles in here, and different wiggles in the spectrum as the starlight passes through the atmosphere of the planet can tell you about the presence of sort of plants or oxygen that came from respiration of plants, or transpiration. I'm not a biologist. Water vapor shows you the presence of maybe liquid water. Methane tells you about feedlots and things like this. But in order to do this, we need really, really, really good precision, really high precision, big telescopes above the atmosphere, particularly ones that are really good in the infrared. So this is what you can see in visible light, but what you really want to see is these things that come from biosignature gases out in the infrared. And so we need an infrared space telescope with really high precision, and NASA has one in the works. It's called the James Webb Space Telescope. It's getting set to be launched in the next couple of years. It's going through late-stage testing and preparation down in Texas right now. It's a 6.5-meter mirror. So the mirror, you can see it's a segmented mirror. The mirror is made of a bunch of mirrors. They'll put it in orbit, and then it will unfold. That better work. 6 meters across. Hubble is only 2 meters across. So the Hubble Space Telescope is this big. So this is the follow-up to Hubble. And you may notice it's gold-plated mirrors, and that's not to be like fly. It's because gold reflects infrared light better than aluminum does. So Hubble has the aluminum mirrors, polished aluminum mirrors. We use polished gold mirrors. And JWST is going to have a tremendous ability to measure the spectra of those planets and see what's in their atmospheres and look for these biosignature gases. Now, just a couple months ago, we're getting real current now, the Exoplanet Science Strategy, led in part by Sarah Seeger, the amazing Sarah Seeger, came out with a consensus study where they said, we know a lot about the planets near the stars, but farther out is harder. It's harder to measure and detect things farther out because they put less signal. What we really need is a wide-field, near-infrared, space-based mission. And NASA has one on the books. It's called WFIRST. It's in the planning stages right now. JWST is getting ready for launch. WFIRST is getting planned, and the NASA just awarded in November a contract to build the tube itself and the mirror. The mirror we already have. It's repurposed from a reconnaissance satellite from the National Reconnaissance Office. So it's a 2.4-meter mirror, same size as Hubble. And WFIRST stands for the Wide Field Infrared Space Telescope. And so the nice thing is, compared to Hubble, if you take an image with Hubble, very, very little fraction of the sky has been imaged by the Hubble Space Telescope. It's been operating for like 20 years at this point, but its field of view is tiny. It's very high precision and can see amazing detail, but it's tiny. It's these little postage stamps on the sky. So here's a nice comparison. My colleague Julianne Dalcanton at the University of Washington, this is her survey, the PHAT survey, P-H-A-T, of the neighboring galaxy Andromeda. And you can see all these little boxes. See all these little boxes? Julianne's survey took a couple years to make. It's just repeated image after image. Hubble images are that big. That's the size of a single Hubble image. So they made this giant mosaic. Hubble image, Hubble image, Hubble image, Hubble image, Hubble image, and they did this for like 2.5 years for the panchromatic Andromeda Treasury, or PHAT survey. Here is the footprint, if you can see that blue line there, or purple line, whatever it is, of WFIRST. That's a single image with WFIRST. So wide field, super efficient. Go take a single image, boom, there's the neighboring galaxy. Move over, boom, do another one. And you can just Hubble image after Hubble image with this new telescope. And it's going to open up entirely new places to look for planets. So here, remember, here's the Kepler. Kepler planets are mostly between Neptune size and Earth size, so the red dots are the Kepler planets here. Remember I showed you that diagonal line. Kepler can't quite find Earths and Venuses, and it can't go out far enough to find Saturns and Neptunes and so on. This is what WFIRST will be able to find with their different planet searching technique. Is they'll find planets farther out, far away from the star, out in the habitable zone, out here 1 to 4 AU. Tremendous amount of increase in our ability to detect planets. WFIRST has one other capability that's pretty exciting, and this is, I'll close out with this. I mentioned that it's really hard to take pictures of planets directly because the stars are 10 billion times brighter. It has been done. This is Christian Marwa, and he went out in 2010 and looked at a bright star and then looked for planets around it. So you can see this dot, that dot, and that dot, that dot, and that dot, this dot, and this dot, and this dot. They went out, November to July. They went out over about 8 months and noticed that these planets were moving. These white dots were moving. Now you're saying, like, where's the star? The star is here. But if you wanted to see something that was like kind of faint next to something really bright, what would you do? You'd block out the star. You'd put your hand in front of it or something. You'd go like this, right? And you'd try and make some more contrast, block out the bright thing. So they use a technique, we call it coronography. Sorry, Denise, coronography. And so you basically put this dot in front of the star, block out the star, and when you do that, light diffracts around the star. It makes an unholy mess where the star is. Look at that. That's all starlight that we were unable to block, not we, Christian's team. But you can get the bigger contrast, and you can see these faint stars next to it. What they want to do with WFIRST is what's called a star shade. And star shade, this is just so amazing. This is straight off the drawing board kind of stuff. This is Maggie Turnbull. You saw a figure of hers earlier. This is a model of the star shade. They're actually much bigger than this. If you make them this like interesting petal shape like this, it shapes the way the shadow looks in a way that improves the contrast. And so instead of looking for something that's 10 billion times fainter, you're looking for something that's 100 times fainter, which is very possible. So the idea is to send up a mission, fly up a star shade, and then go put that star shade out. So here's, say, WFIRST with a 2.4 meter mirror. You go out 50,000 kilometers away and unfold this star shade. You put it in orbit, you move it to that point, and you open it up. And this thing is about 34 meters across. So that's like you could put that in the red zone in Grizzly Stadium, right? So that's how big that is. And then you put it 50,000 kilometers away, and you maneuver it separately from WFIRST so that it's between a star. And you look at it, you cover the star with this thing, and you look at the contrast and look for the faint planets. So they did a desert test, which this amazes me. They built one of these star shades. They went out in the Mojave, set it up here, put a light source in the back. So they put the searchlight back there, put the star shade, covered the star shade, and then put their detector. Here's their detector over here, their camera over here, and then they put a little tiny light over to the side. And see, can we find this light with the star shade blocking this object? And this is the test from Harris Corporation that was doing this work. There's the faint star that's 100 million times fainter than the planet that's being blocked by this star shade. And they showed that this technique can work. There's a lot of challenges here to work out in terms of getting those orbits right and getting the alignments right. But this is the direction NASA is going. So exoplanet missions, just to wrap up. You know about Hubble. Kepler did the surveys and found out planets are everywhere. TESS is finding the nearby ones right now. Webb will go look at their atmospheres. WFIRST will look for the habitable zone ones that are a little further out and identify their masses. And so the goal there is just to continue down this roadmap and start to characterize these planets and look for the ones that might have life around them. Coming soon to a habitable zone near you.
Okay, if you have questions, raise your hands and we'll bring the microphone to you.
Hello, can you hear me?
Yeah.
Okay. I have 2 questions and a comment, if that's all right.
That's very scientific of you.
Okay. So my first question was about the poem. So was it written in another language and translated over? I'm a language major. I'm going to ask these kinds of questions because it sounded very interesting. Okay. Okay. My second question, do you know which company, shoot, I'm blanking on my words right now. Do you know which company was awarded the build the tube for Stargate?
For the telescope I mentioned for WFIRST?
Yes, that's it, WFIRST, yeah.
I just read this. Don't quote me, it might have been Grumman.
Sorry?
It might have been Grumman. The aerospace company?
Okay.
I'm not certain of that. This just happened in November, and that's not on the top of my tongue.
I'm asking because my dad's an aerospace engineer. He
Oh,
works
yeah.
at Ball Aerospace in Boulder.
Ball is very active in spacecraft design, yeah.
And this is where my comment comes from, and you were talking about how you hope that the mirrors unfold on JWST. My dad wrote that software,
Oh,
so I
that's
really
fantastic.
I hope it unfolds too.
That's fantastic. It's amazing, and I certainly hope it works. JWST, the astronomy community cannot wait for JWST. Yes, sir.
I noticed the petal pattern on
Yes.
the test article was different than the one that would be deployed in space. Was that to account for diffraction of the atmosphere that it was sitting in?
No. They're just testing a lot of different designs. I have another slide here that I didn't show. Let's see. What's this one? So basically, what you see on the top here, this is a mathematical exercise, but they go through here and say, okay, let's shape the star shade like this crazy shape, and then look at what the shadow of that looks like. The shadow looks like this, and it's because light diffracts actually, it diffracts around sharp edges. And so if you shape those sharp edges, you can shape the shadow. And so we think of shadows as like you put up a square and you get a square shadow. But if you look real close at the edge of that shadow, you've got like wiggly stuff on the outside of that. And the wiggly stuff matters a lot to astronomers. What we want is high contrast. So here's a weird looking mask. The mask is the light parts. The dark parts is where the starlight comes through. And you get this weird pattern, and you look at that and you're like, well, that's weird. But what if your planet was here? Your contrast is huge. If you can force all of the diffraction into these edges, and then you can just rotate your mask around, and you can look in the dark areas in each one of your images and see if there's planets there. And then you can do stuff like this. The more petal-shaped ones mathematically give you this awesome shape here. Maybe Nicholas can explain that to us. But this is a question of light diffraction and using light diffraction to your advantage. Can you shape the shadow so that you can see it put more light out here and concentrated a bunch of light in here, but it left you this high contrast dark region where you could look for faint planets next to this bright star. So that petal pattern seems to be one mathematically that they're converging on. And they're trying all kinds of different shapes, like the one that Maggie's showing in her hand here.
Can you tell me what the nearest star to us that they found exoplanets at would be?
Yeah, that's the next nearest star, Alpha Centauri A. The star Alpha Centauri A is in a triple star system called generally Alpha Centauri. So it's Alpha Centauri A, Alpha Centauri B, and, just to be different, Proxima Centauri. And I'm just going to air a grievance. That's the thing we do. I'm going to air a grievance here. I was on a trivia night once with a bunch of music majors, and it was 2 astronomy majors that were with all these musicians. And one of the pub night trivia question categories was astronomy, and they all looked at me and Adam. And we were like, oh, wow. And we got 10 out of 11 questions right in that round. And the one we missed is, what's the closest star to the Earth, other than the Sun? What's the next closest star? And Adam and I looked at each other and thought, oh, we're hosed. Because it's Alpha Centauri, but Alpha Centauri is 3 stars, and the one that's nearest to us is called Proxima Centauri. They looked it up on Wikipedia, and they just wrote something down. We had to guess and we guessed wrong. So we went up and argued, and the pub trivia guy's like, go sit down. So Alpha Centauri A is one of the 2 stars, 2 bigger stars in there, and it has a planet orbiting it, which is pretty amazing. And that's only 4 light years away. Yeah, I don't know much about that planet because I should be better read on that, but there is one there. And I don't think it's habitable zone. I think it's closer into the planet than that, so it's pretty warm. It'd be like a baked ZD of a planet or something, but I don't know the details. But you can look it up, Alpha Centauri A. So the planet is Alpha Centauri A little b. Saw a hand, yeah.
100 years from now, could you speculate on the science of where this is going? Are we communicating? Are we confirming life?
That's a whole other talk I would have loved to also give.
Yeah.
And part 2 of this talk is the Drake equation and the Fermi paradox, colonizing the galaxy and how fast that would happen. The thing about technological development that's amazing is how rapidly it happens. The iPhone is 11 years old. When I was an undergraduate, which, contrary to what some of my students think, was not that long ago, I carried a pager so that my girlfriend at the time could call me when she had a break at work. And it's just fascinating to think of that technology. And my friends were like, ooh, you have a pager, cool. It's like, not so cool now. But yeah, the iPhone, when we were, not that long ago, we were like, hey, wouldn't it be neat to call grandma and be able to see her? It turns out that's free, and we get annoyed if it doesn't work, right? And that's 10, 12, 15 years. So if you try to imagine the decadal surveys, we have a time horizon of 10 to 15 years is what we're thinking on that. Like, by the end of the next decade, what should we be building for use the following decade? That's kind of what we're doing in astrophysics when we do these surveys. And things like these star shades, like what Maggie's holding up here, these are, at XOS, if that mission goes, this mission would be 2025, 2027, 2030. WFIRST, we would hope to launch in like 2025. JWST maybe next year. JWST was like a high priority in the 2000 decadal survey. The Hubble Space Telescope was planned in the 70s, launched with late 80s technology, and is still up there today. We've been able to swap some things out because of the shuttle program. So our sort of technological horizon is sort of 15 years. So if you want to start talking about 6 generations of technological horizons out, what could we be doing? I'm going to go back to Paula Scotti, one of my professors, my STARS professor when I was an undergraduate. We were talking about asteroids coming at the Earth and extinction level events, something the size of Mount Sentinel, paralleling 30 kilometers per second at the Earth. What do we do if we find one of these in these surveys that are looking for them? And Dr. Scotti said, oh, we'll just fly something up there and push it out of the way. And like her just sort of like, don't worry about it. The key thing is finding it. Was sort of like, well, I guess if it's an extinction level event, we'll figure that out, one would hope. But like the advancement of technology is such that it's really more a question of like, what can you dream to do? One thing that would be really great is to not have to fight our atmosphere for all these measurements that we make. Astronomers like to say, unfortunately, the Earth has a habitable zone atmosphere because we have to look through it and it muddies all of our imaging. It'd be really nice if we could put nice precision telescopes on the moon. If we had a moon base to do these observations. I would love to have humans go to Europa and Titan and burrow down through the ice and see what's down there, see if you can get down into the liquid water. Look around. Yeah, see if you can find the squid. So 100 years out, I think that's sort of the future of astrobiology. It's like, go visit these places. Mars, I think, is a good test bed to see what's going on. We have these rovers running around on Mars. When I was an undergrad back in the late 90s, we had Sojourner, which is the size of my laptop, cruising around on these little Lego wheels and sending back pictures, and it was bloody amazing. And now we have like something that's the size of like, it's bigger than a Prius driving around. It's called the Mars Global Explorer, Mars, I can't remember what it's called. Phoenix? Is Curiosity, George, is that the big one, the newest one? I think that's the previous one. That was the mid-sized one. It's the one that had the 7 minutes of terror, the one they lowered on the, why can't I think of the name of that? No, Spirit and Opportunity were the small ones. Maybe it is Curiosity. I think it's Curiosity. I think George is right. George is an astronomer, so I trust George. So, it's that's a big advance, and that's running around. But those have only, over the course of all the time they've been on Mars, run around 30 kilometers, 50 kilometers over 18 years or something. So solar system exploration, I think, is a big direction that astrobiology is going to go. As far as the exoplanet stuff, we'd like to get out and do space interferometry missions, go up and take 2 telescopes and put them some distance apart and look from 2 different angles and do parallax measurements and combine the light, interfere the light with itself and get really high precision small measurements of things and measure the radii of the planets very directly. That would be really neat. It'd be great to survey all of the stars, not just the 200,000 nearby bright stars, but let's go do 300 million of them. And that sounds crazy, but there's a satellite called Gaia up right now that just took us from measurements with Hipparcos of the distances to stars. We knew something like 150,000 stars. We knew the distances to real well in the 1980s, and now we have the distances to 1.4 billion stars with the mission that launched about 5 years ago. So that technological curve, it's like Moore's Law. It goes like this. So it is really hard for me to just stretch my puny human brain more than 20 years out into the future. People like Sarah Seeger are paid to do this and are thinking about the direction that we're going to go. I should have been better prepared for that. Great question.
I was going to say, I had a question exactly about that
I know that
planning.
voice. Yeah. Hi, Eileen.
I mean, in my own field, I can't imagine getting together and deciding what we would look for at any time. So is it that it's a smaller group and you've just agreed for so long on how to move forward? Because if that's the case, I would think, for example, climate scientists could learn from that as well. I mean, how do you manage that process?
One thing that helps us is we're a small field. My roommate in graduate school was a chemist, and he would go to his conferences, and 35,000 people would show up at the conference, and it's held in like a small city in Kentucky or something. It is a small city in Kentucky. I go to a conference, and like all 4,000 astronomers in the world are there. We're a small field. There are something like 2,800 American astronomers in the United States community of astronomers. We have meetings every January where probably 2/3 of us go to these meetings. And we tend to come to consensus. And it's not to say we don't argue and people don't get angry and people don't get what they want. But we know that taxpayer dollars are limited, they're hard to get, and we need to use them wisely. And so it's probably best for us if, as a community, we can present a unified face and say, this is what we agreed on. We argued, we don't all totally agree with everything here, but this is what we've decided we're going to ask for. And we prioritize things, and we say, if Congress gives us a lot of money, we'll go this far down on the list. But if they only give us this much money, we're going to do these things. And we're all going to agree on the priority rank of those. And so we do one of those every year, and right now the 2020 survey is in preparation. It'll come out next fall, in 2020 in the fall, like a year and a half from now, and say the direction that we want to go. I can't speak to like biomedical community, psychological community, or anything like that and say how they would do that. Those are much bigger communities than us. But we are almost entirely taxpayer funded. Unlike the chemistry, the field of chemistry, where there's industry and there's pharmaceuticals and people sell money for profit. There's not a lot of profit in astronomy, at least not for those of us doing it. Ball aerospace maybe, but that's something that we've decided to do in response to our constraints.
The studies that you've been talking about are looking for life forms that fit within the parameters of life as it exists on Earth. You know, the temperature ranges and the availability of water and so forth and so on. Are there astrobiologists out there that are thinking outside that box?
Absolutely.
And thinking about what life forms might exist out there that come from a completely different set of factual assumptions?
Absolutely, and I don't know if you were here for Nancy Hinman's talk 2 weeks ago, but Nancy discussed this a little bit, the idea of like silicon-based life forms and things like this, or why we choose the directions that we do choose to like look for liquid water, look for carbon-based life forms, look for organic molecules that can form long chains. I know Nancy talked about that in great detail, the hydrocarbon chains that can make these very complex molecules, things like proteins that can fold and do enzymatic activities and things like this. I'm about done with my biology with those couple sentences. What we're looking for here in my field is substrates. We're looking for the planets to host biology, and then in the next decade, next 15 years, we're trying to use JWST to identify if there's any signatures in the atmosphere that biotic activity is occurring on those planets. We need the biologists to tell us what those signatures are. What should we be looking for? We can develop the technological capability to look, but I'm not a biologist, right? So we don't do the biology. We're looking for the worlds. I think it's interesting. One of the amazing places, and Nancy probably would agree with this, to do astrobiology on the Earth is Yellowstone. What an amazing laboratory! You have these like crazy environments where these crazy you look at as was a grand prismatic spring has those beautiful colors. It's all the different colonies of bacteria. I'm just sort of repeating what little I remember from a great talk I heard by an astrobiologist here on campus. And you're looking at different life colonizing different things. Anything that can hack out a living in this extreme environment, as soon as it's the best, it takes over. And so evolution will provide. And so if there are substrates available, there's places to do this biology, the evidence seems to be biology will find a way to do that. So as far as are we looking for sort of things, it's life, Jim, but not as we know it kind of things, like Dr. Spock, live long and prosper. Yes, people are doing this, but I'm not actively involved in that work, so I can't speak knowledgeably. If Nancy's still around, I'll volunteer her out in the foyer. Yeah.
To reverse our perspective, what kind of transmission or footprint does Earth leave with the radio and TV transmissions for, 80 or 100 years now? Are we leaving much of a beacon or a calling card in the universe? So there's a couple ways to look at this. There are biosignatures on our planet. The presence of the O2 molecule, oxygen in molecular form in our atmosphere, is unusual. If you started a planet under Earth-like conditions and poured a bunch of oxygen in its atmosphere, it would oxidize everything. Oxygen's super reactive. And so you would end up with rust and things like that use oxygen. The presence of oxygen in our atmosphere tells us there's a continuing source of oxygen in our atmosphere, and that's plants. It's plant life. It's biotic in origin. So to that extent, oxygen is a biosignature gas. Is that a very good biosignature gas, oxygen? I mean, there are other ways you can get oxygen. There are better biosignature gases than that, but that's like an everyday example for us. The oxygen we breathe came from plants, and without the plants continuing to provide it, that oxygen would go into other chemical reactions. So there are signatures in terms of the biosignatures that we have. The presence of liquid water is highly suggestive.
So the water vapor in our atmosphere, if Earth transited the sun from some alien civilization looking through our atmosphere with their W first or their JWST and looking back and seeing Earth transit, and they would do transmission spectroscopy, they'd find water vapor in our atmosphere, they'd find CO2 in our atmosphere. And that's suggestive of life. It's not the only way it can get there. But then again, we're also squawking. So since the 1930s, we've had television signals. Earlier than that, we've had radio signals on the air. They're faint. We're not beaming anything out. There are good discussions to be had here as humans have only had the capability of detecting our own radio signals for 90 years or so. So any civilization that's at least as advanced as us is probably way ahead of us. And so if there's like really powerful civilizations out there that can do everything that we can do at least to detect us, and possibly who knows what more, talk about going 100 years out in the future, like go 10 million years out in the future, some star child out there receiving these signals, like do you really want to be the bird that just learned to sing and is like, hey, I'm over here? So there are real questions about that. Should we be beaming our presence or should we just listen? And the Search for Extraterrestrial Intelligence community has pretty much decided on a strategy of just listening. We don't beam radio pulses. We don't shine laser. We don't flash Morse code or pi or something at neighboring planets. I mean, we know of places that have exoplanets, and some of those could be habitable. There could be somebody there. You could flash the messages and see if they respond. Light travel time, that could take 150 years or more. But it's probably not a good idea, because if they can receive it, they're at least as advanced as we are. So there are interesting philosophical questions to be asked here.
So tomorrow when you talk to your friends and your colleagues and people at coffee or when you're at work, be sure to tell them that you went to the lecture series that was out of this world. Big thank you for our speaker tonight. Come join us in the foyer for some refreshments and an opportunity to talk with the speakers. Thank you all for being here this year. We appreciate your support.
Just a couple quick announcements. One, Jeff's touched on this a little bit earlier, but we want to thank the original committee members for conceiving of the community lecture series and their invaluable service. Ann Boone, Chris Comer, Linda Gillison, and Don Hobby. They recently retired from the committee, but we have a great committee that has joined the committee, and they're doing a great job. Jeff Badnock, Joe Batts, Kitty Robbins, she's also an original committee member, Peggy Coor, Jenny McNulty, and Robert Stubblefield. We hope that we can continue this for another 20 years because it's a remarkable thing to showcase our amazing faculty. And with that, I'd like to extend a personal thank you to the faculty that joined us this year. Nancy Hinman is here tonight, Nate McCrady, Steve Running, I don't think he's here tonight, Mike Mayer, Anna Clenny's here, and Rob Browning. So thank you very much for all of them coming out and sharing their knowledge. And the last announcement is that we're heading into our 22nd season, as Jeff mentioned. We want to know what you want to learn, what you want to see, what's going on here. And this program would not exist without the support of our members and our alumni and friends in the neighborhood that come out every year and do this. So thank you to all of you. And that's it.